Just wanted to add my welcome to Andrew's. My name's Randolph Kershane. I'm one of the co-directors here of the MIT Concrete Sustainability Hub, and thank everyone for joining us at one of our public webinars. Many of you know that over the last 10 years or so, the Hub has been doing a lot of research to put together the data and tools to understand the environmental impacts and economic impacts associated with different technologies and operational strategies, maintenance strategies for the U.S. pavement network. And over the last couple of years, we've been applying those tools to look out into the future to better understand what are some of the options for continuing to drive down the carbon footprint in particular of that system. And so today, Dr. Hassam Zari Jafari, one of the postdoctoral associates here in the Hub, is going to share with you some of our learnings from that work. So with that, I'm going to turn it over to Hassam. And thanks again for joining us.
Thank you for the introduction, Randy, and thank you everyone for joining this webinar. Today, I'm going to talk about different strategies for achieving carbon neutral mixtures in the U.S. pavement network. And for the purpose of this presentation, we are focusing on the embodied impacts of the materials that are being used for the pavement maintenance and repair and reconstruction. So to start this presentation, I want to talk about the motivation of this research that we observe in different research reports and in different projections that the role of materials, specifically construction materials, in the total GHG emissions of the world is increasing. As you can see on the left chart and on the brown part of this chart, this stack chart, construction materials comprises a huge amount of GHG emissions, and it contributes significantly to the total GHG emissions of the materials being used. And this contribution has been increasing since 1995. That you can see at the beginning it was around 15%, but now it's around 23% of the total GHG emissions from the materials. And in light of different strategies and proposals to achieve net zero operational impact for different infrastructure systems such as buildings and pavements, we expect that the role of materials in the total GHG emissions is going to be more important. And when we talk with different people about different strategies to decarbonize the construction industry, we see that the construction industry is generally perceived as a hard-to-abate sector. And we read different interviews and we watch it in different medias that they are talking about replacing every single infrastructure in the supply chain of these construction materials. For example, this quote that I got from an interview of Bill Gates in The Guardian, that he is talking about replacing every steel and cement factory. But is it really the case when we are thinking from an engineering point of view? Do we have only these solutions to replace all the cement factories and elevate the technology or improve the quality of these plants to produce these materials? To answer these questions, I'm going to go ahead and talk about different ingredients of the mixtures that we use for pavements, both asphalt and concrete constituents. And we see that based on as pavement is a composite materials, we can have different constituents, and each constituents will give us different opportunities to reduce the GHG emissions of the embodied impacts of pavement materials. For example, from the coarse and fine aggregates, we can produce synthetic aggregate to utilize the captured carbon permanently in the aggregates, or we can use recycled materials as a replacement of the virgin aggregate in order to avoid the GHG emissions related to the manufacturing of the aggregate. Or from the binder perspective, both for asphalt and concrete, we can increase or we can utilize more recycled content, or we can sequester carbon and we can store it in different tanks, or we can use it as, like I said, in the aggregates, Or the other important parts which needs more engineering insight is about increasing the packing density, or in other words, optimizing the binder content in the mixture. And therefore, we use less materials and less GHG intensive binder for our asphalt or concrete mixture. For concrete, we have one constituent as water here. So we can, with the recent research and implementation efforts, we can see that we can use the captured CO2 in the mixtures, in the fresh mixture, or we can use it in the water of the concrete mixture. This is another opportunity to offset the GHG emissions of the concrete mixtures. Or the recent technologies that have been that different researchers have been working on in the last 3-4 decades is about chemical admixtures to improve both the performance, or for example reduce the demand, for example energy demand, for example from war mix asphalts, or increasing the mechanical properties of the concrete mixtures by incorporating superplasticizers and reducing the water cement ratio. So when we look at the national industry reports, such as National Asphalt Pavement Association reports or the National Ready Mix Concrete Association's EPD program, we can see that some of these embodied solutions have been already implemented. For example, we can see that alternative binders have been already incorporated from 13 to 23% of the total binders in the concrete mixtures around the US. And we can see that, for example, for the electricity grid, some regions have been using and have been leveraging renewable sources of energy. So the GHG intensity of the energy produced in that region, in those regions, are much more better than the others. Or, for example, reclaimed asphalt pavements or asphalt shingles have been already incorporated, in a variety of percentages from 0 to 28%, or war mix asphalt have been already reported up to 100% incorporation in the new asphalt production in different locations. So we can see that we have seen some efforts, mostly motivated by the economic aspect behind that. But when we are seeing the GHG emissions associated with the asphalt and concrete mixtures, including those efforts and solutions that have been already implemented, we see, first of all, a diversity of the carbon intensity for the concrete and asphalt mixtures, and we see that we have a long way to achieve carbon neutrality for asphalt and concrete mixtures for our pavement network. Currently, the majority of the pavement network is surfaced with asphalt, so it's very important to incorporate asphalt in the analysis. On the other side, we have concrete as a durable materials that have been implemented as the pavement surface layer for several years now. So it's very important to incorporate both of these materials in the analysis, and to see, should we intensify the current implementation levels that I showed you in the previous table, and the intensification of this levers or solutions, are these enough to achieve carbon neutrality, or do we need to add new solutions to the current ones? So to answer the questions, we define this objective to propose a comprehensive pathway to achieve carbon neutrality for the US pavement network by 2050, in compliance with other guidelines and proposals for carbon neutrality achievements. So to do that, we needed a huge amount of data. First of all, to collect all this data from different road segments, from publicly available national databases, to see what's the current condition of the roads in terms of the surface deterioration levels, what's the traffic level, what's the thickness of the pavements. And we also need to predict the future behavior and the required amount of maintenance and repair actions, and the associated materials as well, which we call in the context of material flow analysis for this pavement study. And then we have a segment level calculation of the road performance based on the data that we got from highway statistics and long-term pavement program databases. And with the application of the maintenance and repair actions under a constrained budget for each state, we could get the bill of materials. And with the bill of materials required for pavements, we needed some life cycle inventory, and we could collect some of the data from, again, the industrial organizations such as NAPA and NRMCA to have a good representative concrete and asphalt mixed designs and the incorporation of different materials in different regions. And at the end, we could calculate the annual GHG emissions of the materials in the future. Here for this study, we considered an analysis period from 2017 till 2050. So what do we get from this study? First of all, we found that carbon neutral, or in other words, net zero mixture are feasible both for asphalt and concrete. The other point is that pavement stakeholders should get involved from different levels and from different parts of the supply chain. They should sit together and make this decision how to achieve this carbon neutrality and how to collaborate with each other to achieve this goal. And the other important insights that we could get from this research was that the carbon neutral solutions are interdependent. So the effectiveness of one solution may depend on the others as well. And I will show you with examples and details as well. And at the end, the optimal pathways can be selected through an eco-efficiency assessment. In other words, it should be jointly done with an eco-efficiency assessment, not to waste or not to overestimate the price of carbon neutrality achievements. So for that purpose, I'm going to start with the scope of this analysis and think about and describe the projected attributes and some of the carbon neutral attributes that we have designed for this study. For the project attributes I can name those as those solutions that have been already legislated and predicted in the future. In other words, we can see that in different locations, we have different goals and different milestones for achieving specific amount of alternative binders or carbon capture and storage, for example, for chemical production, or the energy demand and the GHG intensity related to the energy for both heat and electricity, which are mostly related to the supply chain engagement state. But we broadened this and we included the designers and end-of-life managers to achieve a better solutions or carbon neutral solutions here. First of all, we consider the design optimization. So this is the role of the designers to improve the quality of design based on the available data and the historical data that they have, to refine the process of design based on new codes. And we have supply chain, so we expanded the solutions in the supply chain to gain benefits for example, binder intensity, the carbon capture utilization for aggregates, in addition to intensifying the other levers that we have in the projected attributes. And at the end of life, we have this recycling that we can intensify and increase as well. So to go through the details of these solutions, I would like to share this table with you to see how we have implemented this solution. So first of all, what I would like to emphasize here is that with the dynamic framework that we have defined here, we can implement the rate of implementations of these solutions in the future differently. In other words, we know that the next day next year wouldn't be possible to reduce 22% of the asphalt geometry or, for example, thickness, but we need to gradually implement it in the future. So with this dynamic modeling would give us this opportunity not to overestimate and not to make exaggerated cases in the future. So let's start from the first solutions here, pavement design optimization. We expect 22% reduction for asphalt and around 18% reduction for the concrete based on the optimization of the pavement design. These are the data that we could collect from the experiences of different DOTs once they shifted to a new method or new approach for designing their roads, changing their structural number base for a couple of states, saved a lot of asphalt for their pavements. The other one, alternative binders, in 2050, it was estimated around 40% binary mixture, like including Portland limestone cements and other supplementary cementitious materials. But in the ambitious scenario, we can see the opportunity of including ground tire rubber, here referred as GTR, up to 50%. And we can also see some observations in the pilot projects up to 50% increase of the alternative binders in the mixtures. For the transportation and electricity, we relied on the energy outlook reports, but for the ambitious scenario, we assume that we can supply the energy demand for the supply chain of cement, concrete, and asphalt by full renewable energy sources. The reclaimed asphalt, we can see that in conjunction with the GTR, we can also incorporate up to 50% reclaimed asphalt pavement without compromising the performance, the long-term performance of the asphalt based on the test results. And war mix asphalt is conventional 100% was assumed by 2050 as well. And for the CCS in the kiln for concrete, we consider the global average achievement by 2050 for the US industry. But for the carbon neutral, the best performance, like the oxy-fuel technology was assumed here as the basis of the assumptions for the carbon neutral solution. For binder intensity, around 7 kilogram per cubic meter per megapascal can be achieved by this compressive strength level, the conventional compressive strength level for concrete mixtures. And once we sum up all these savings together, we found that we still need to offset a proportion of these emissions to achieve net carbon neutral mixtures. And we try to implement the carbon capture utilization for aggregates to some extent to achieve carbon neutral asphalt and concrete. In other words, we need 23% of our total aggregates produced by CCU technology for asphalt pavements to have net zero or carbon neutral asphalt. And for concrete, it's around 66% of the total aggregates that needs to be produced by this technology to achieve carbon neutral asphalt. Concrete, sorry. So here is the projected results, those solutions that have been legislated or have been predicted in the future for different road types that you can see on this screen. On the y-axis, you can see the annual embodied GHG emissions of the pavement materials. Different colors shows different road types starting from interstates, arterials, collectors, and locals. And on the x-axis, you can see the year starting from 2017, finished by 2050. One important thing is that under the projected scenario, we don't see any reduction, significant reduction in the future because of the increase in the demand for the asphalt and concrete material as a result of the climate change impact, faster deterioration of the network, and also to some extent the network deterioration for different locations. But what we see here is that we have almost equal opportunities for different road authorities, starting from federal governments to state DOTs and to cities, municipalities, and private owners to offset these GHG emissions. Therefore, they should sit around one table because they all have significant responsibility to reduce the embodied GHG emissions of the road network. So that's one point that I would like to emphasize here is that we have to consider all these stakeholders together, both from the management point of view and the other parts from the supply chain, starting from the design up to the end of life. So, but when we look at the mixture level calculations, you can see here on y-axis the kilogram CO2 per cubic meter of concrete, and in the x-axis it's again the year. Under the projected scenario on the left chart, we can see around 15% reduction of the GHG emissions of the mixtures under the projected scenario. But for the ambitious scenario, like I said, we set the total amount of CCU aggregates in a way to achieve carbon neutral mixtures by 2050 in light of fully renewable energy supply for materials and concrete production. But if we don't consider this full renewable sources, and if we rely on the projected improvement of the energy supply, we can see that it's hard to achieve carbon neutrality by 2050. Therefore, one indispensable part of this carbon neutral solutions is renewable energy supply for the whole supply chain of the concrete. When we are looking at the asphalt pavement, we can see that in the future, we have around 10% reduction on average for the embodied impact on the projected scenario on the left figure. But once we are seeing the ambitious scenario on the right part under the renewable energy assumptions, it's fully satisfied. Again, if we turn off the renewable energy, we can see that it's really hard to achieve carbon neutrality under the current solutions in the future by 2050. So we here conclude that both for asphalt and concrete production, the renewable energy supply is very important and should be considered in the calculations and in the strategies and policies for carbon neutrality achievement. So let's go see the cumulative GHG savings of asphalt and concrete during this 34-year analysis period. Here we can see the cumulative GHG emissions of the asphalt during this period. On the y-axis is the cumulative embodied GHG emissions from 2017 till 2015 in terms of million ton CO2 equivalent. The first and last columns show two different scenarios, the 2017 level, if we don't see any improvement in the future, and the last column is the ambitious or the carbon neutral solutions that we propose here. And in the middle, you can see different solutions that we propose that was implemented from the bottom to top. First of all, optimization was implemented, then RAP, WMA, transportation and electricity, alternative binders, and at the end, carbon capture and utilization for aggregates. We can see that for asphalt, we expect 48% reductions of the GHG emissions during this analysis period by 2050. But for the concrete mixture, we can see that although the total GHG emissions, comparing the first 2017 level column on the left and this one, we can see that concrete is almost 1/10 of asphalt because we use less concrete for the pavements, but the level of reduction in concrete is more pronounced, 58% reduction, owing to the benefits that we can get from the carbon capture sequestration. Up to 36% of the total savings comes from the carbon capture and storage. One important lever or solution which is similar in both for asphalt and concrete is the carbon capture and utilization, which plays an important role, like I said, to achieve carbon neutrality. And to talk briefly about this carbon sequestration, we can sequester the CO2 from any different industry, and we will mineralize this CO2 using different alkaline reactants. So it's very important for us to have enough alkaline reactant to be available in different locations, and then we have aggregate production, the synthetic aggregate production for for this CCU aggregate strategy. We did this analysis to make sure and to understand if we have enough aggregates provided in different locations of the US for the purpose of this carbon neutrality scenario. And we see that in different locations, we need different amount of aggregate, but when we sum up the total amount of mineralized CO2 product, it's gonna be around 6.5 million tons of aggregate. On the other side, we considered 3 different alkalinity sources, which is mostly magnesium oxide or calcium oxide sources, for example, the desalination brine potential, municipal solid waste potential, or mine tailings, the ultramafic mine tailings, and we estimated the amount of materials that can be available for CO2 mineralizations based on these waste or byproducts from 2017 till 2050. And when we compare these two values, we can see that, well, obviously we have a lot of resources available for CCU aggregate production. So here is about the alkalinity sources, and now we are talking about the prioritization of the implementation. So like I said, we can define different solutions, but what would be the best order of implementation? Should we first implement alternative binders, or then binder intensity and then carbon capture storage? What would be the basis based on a best solution? It's important to select an appropriate pathway, because the level of implementations and the order of implementation both can affect the total savings and the total contribution of each lever to the total savings. So to give you a simple example here for concrete, imagine that you have a concrete mixture, 400 kilograms Portland cement is being used per cubic meter of concrete, and we don't have any SCM. And we assume that for this purpose, for the simplification, 1 kilogram Portland cement is equal to 1 kilogram CO2 emissions. Once we implement, for example, alternative binders, 50% Portland limestone cement or supplementary cementitious, we will remove half of this emission, so we have 200 kilogram savings of GHG per cubic meter concrete. The second solution that we would like to implement here is the binder intensity. Imagine that we have a better aggregate gradings, and we would like to improve the binder intensity from 400 to 300 kilogram binder per cubic meter mixtures. We can see that we remove 1/4 of the previously available or previously emitted GHG from the concrete mixture, which would be around 50 kilograms CO2. And summing up these two savings will give us 250 kilogram saving per cubic meter concrete. While on the other path, I would like to first implement binder intensity. So 400 will turn into 300, therefore we will have 100 kilogram savings, because we have removed 100 kilogram Portland cement. And in the second stage, when I'm implementing the alternative binders, in other words, 50% replacements of the available binder, which is around 300 kilogram in this example, I have saved 150 kilograms CO2. We can see that again, when we sum up 100 kilogram here with 150 kilogram here, it's going to be 250 kilogram, but the level of implementation and the prioritizations of each level would give us different contribution, 200 kilogram for alternative binder here as opposed to 150 kilogram. Therefore, it's very important which level or which solution is implemented first. So to give you a broader example, you saw this graph here, the left one, which is related to the cumulative savings of concrete mixtures used for pavement network. Here, the order of implementation is from the bottom to up again. Here we have optimization implemented first, which will save 16% of the total savings that we can expect from all these levels. Then 36% savings from carbon capture and storage. If we implement carbon capture storage first, we're going to get 42% savings from CCS, while the total savings will stay constant. That's because the optimization solutions have been implemented first. Therefore, we have, let's say, a thinner concrete slab, and therefore we need to use less concrete in the future, therefore less cement and less carbon capture and storage here. And when we are looking at, for example, asphalt mixtures, here we see that again optimization was implemented first and carbon capture utilization was implemented as the last lever. Here the CCU contribution to the total saving is 30%. Here is 5% when we are implementing CCU right after RAP. And the reason is that here transportation and electricity has been already implemented. In other words, the grid has been already decarbonized intensively. Therefore, we expect a larger savings from carbon capture and utilization. On the other example, we are not leveraging a decarbonized grid, to supply the required energy for carbon capture and utilization here. Therefore, we expect a relatively smaller amount of savings from CCU, but the total savings from electricity would be even larger. Therefore, it's very important for us to find a near optimal or optimal solutions to reduce the cost of implementation here. And for that, we definitely need to have an analysis of the embodied GHG abatement cost, as you can see on this graph. On the y-axis, I have the embodied GHG embodied GHG abatement cost in terms of dollar per ton CO2 savings. And on the x-axis, you have cumulative GHG savings of the solutions that we proposed here, both for concrete and asphalt. First of all, you can see that the total cumulative saving is around 230 million tons CO2 during this analysis period. The other important factor and observation that we can have here is that alternative binders, wrap, binder intensity, and optimization will not only save CO2, but also save project money for us. In other words, it's like a double win, both from the economical and environmental aspect, which will be around 52% of the total expected savings from all these solutions. Therefore, we can go up to half of the way without even spending a dime, or even we can save some money for different locations, but we just need to change our insights related to the design and the incorporation of the materials and loosen the standards, or develop new standards for these materials and moving toward performance-based specifications. So here, what I would like to recommend and share with you for reducing and achieving carbon neutral mixtures, both for concrete and asphalt, is that we definitely need to have the efforts from the industry to install the best-in-class technologies for their supply chain. And we definitely need to have more mature CCS technologies to lower down the cost and making more attractive for the cement industry, or for example aggregate production. And we also need to ensure the sourcing of renewable energy, both for heating and for electricity. Heating is important for asphalt industry, and therefore it should be included in this projections. And performance-based standards, we see some recent good efforts of developing new ASTM standards for hydraulic cement and, for example, supplementary cementitious materials. But we definitely need to go further, and we have to have performance-based standards for the whole mixture as well. And the other important points about low-cost synthetic aggregate production, we definitely need to support research and scale up the industry and the technology and lower down the cost as well to achieve carbon neutrality. And if we have different tools to identify low GHG mixtures, it would give us a better opportunity to evaluate the solutions and the implementations that we have, or if we can design our road systems in a better way based on the historical data and the experiences that we have observed from these data. And evaluating the use phase impact, it's very important for us to consider that what if we implement this carbon capture utilization, is there any consequences related to the performance of the mixtures? So we definitely need to have more insights about the use phase impacts and the longevity, or for example, the durability of the mixtures, and producing resilient structure that can resist against major events in the future. Or for example, for concrete, enabling carbon uptake in concrete, for example, for both the use phase and end of life. And at the end, while we are considering the embodied impact solutions for pavement, we can see that there are multiple opportunities throughout the life cycle of the pavements related to the construction, use, and end of life. We can use better equipment. We can use cleaner energy for construction equipment. We can make our road stiffer, smoother, and more reflective, or we can increase the carbon uptake both for the use and end of life, or we can use or reuse the dismantled elements for other applications to give a second life to that material as well to achieve carbon neutrality. With that, I would like to again repeat the same key messages that we have. Carbon neutral mixtures are feasible in the future, but we definitely need to sit together with different pavement stakeholders at different levels to get them involved in the decision-making process and find the best solutions for each authority. And then carbon neutral solutions are interdependent. So once we are analyzing them together, it's very important to consider the implementation prioritization here. And the optimal pathways can be selected through an eco-efficiency assessment, like I showed you in the GHG abatement cost curve as well. With that, I would like to thank you for joining this presentation, and I'd be happy to take any questions as well.
Thank you, Hassam. It looks like we had quite a few or handful of questions here pop up while you were talking, so maybe I'll just sort of walk you through those and
thank you.
Get your thoughts on them. The first question that came up was, have you worked with the Envision credentialing system, the system that was developed by ASCE and the Institute for Sustainable Infrastructure? And I guess, how would that interface with the kind of work that you're reporting on here?
I unfortunately have not any collaboration or any work with this certification system, but I would assume that following the principles of the certification systems, it would focus on the embodied impacts reduction of different materials. What I would propose for this certification systems, along with the recommendations that we have in one of my latest slides, was that it would be important to incorporate the use phase savings and the efforts that different authorities will go through to make the road smoother, stiffer, and more reflective in the future. So it hasn't been, the use phase savings hasn't been recognized in this certification systems, but I think it's an important point to include.
Yeah, I think I guess I would add to that. I mean, my understanding of Envision is that it touches on other issues too, as beyond carbon, which are certainly important. I mean, our focus here has been around a quantitative estimate of CO2. And although the presentation today focused on embodied, I think it's really important to emphasize the point that Hassam just made, that these kind of systems shouldn't only be ever evaluated considering their life cycle impact. Moving on to the next question, you made reference to changing the material mixtures effectively as one of the key strategies. And the question is, are there good accelerated testing methods to confirm that the performance or durability of new materials are equivalent or better than current ordinary Portland cement or ordinary asphalts? Why don't we talk about that first, and then there's a second part to that.
Sure. I think that's one of the important parts of the acceleration for the implementation of these solutions. Currently, there is limited information related to the long-term performance of these materials. Therefore, having a set of standardized solutions and prescriptions related to these materials would definitely help to start in the short term. But in the long term, the research and development in this area would definitely contribute to the maturity of the market and the implementation as well.
Yeah. So maybe another way to say that is I think accelerated testing is a challenge. So it's important to kind of get on this now in order to get testing in place. Having said that, there are instances where alternative pavement materials are already in place. So I think it's important to leverage the testing that's going on in other locations. So the second part of that question was if just scrolled on there. If the materials are less durable, does the modeling that we've done account for the frequency of kind of recycling, or I think if I just generalize that question to rehabilitation, reconstruction, How is that kind of built into the analysis here?
Absolutely. It's a great question. It's again getting back to the importance of the solution selections based on the life cycle performance. If
Mhm.
we compromise the durability or the long-term performance of our pavements with the implementation of these solutions, maybe it's not a viable way to reduce the embodied impacts of concrete, because we definitely use more materials in the future if it compromise the performance. So whatever solutions that we plan to implement should be jointly assessed with the performance or the predictions of the future behavior of the
Mhm.
road segments.
And Hassan, the analysis that you showed is built on a model that is simulating that rehabilitation, reconstruction. In other words, it is accounting for future materials entering the system. Um,
Absolutely.
the next one, I don't think we have too much to comment on this, unfortunately. But I don't know if you have thoughts on it. Asphalt is now made from fossil organics. Is synthetic paving material with similar characteristics possible? I think this is generally outside of our area of expertise. Any
Sure. For
comment
example,
or two?
I we have considered ground tire rubber here as a recycled materials, but biosources of binders for asphalt pavements are currently under investigations, and I think it would be a solution if we can find a way to standardize and scale up this effort as well.
Yeah, that's not really kind of a focus of ours. The next question here was actually about the research brief. Somebody did their homework ahead of time, apparently, and asked. So we assume the question is basically about the availability of alternative cements and SCMs. So we assume that there would be possible to increase the use of Portland limestone cement, slag, or make use of slag and fly ash. But of course, fly ash in particular, there we anticipate it to be essentially phasing out as coal power production declines. This individual also points out that with a shift to the electric arc furnace, there would likely be a decrease in the availability of slag. Um, so, how do we see this kind of impacting um, the results? And also, they mentioned IEA considers calcined clay. Any thoughts on that? So maybe just comments about availability and yeah.
Sure. Yeah, that's a great question as well. And I think it's timely because with this decline predictions in this in the availability of these conventional or already prescribed SCMs, we might be concerned about the long-term availability and market availability of these materials in different locations. But one of the benefits of this performance-based specifications of the materials is that as long as the contractor or the producer can satisfy the performance, they can use different types of materials, and it will encourage the innovation in this area. Like recently, the implementation of calcined clay with limestone as a ternary blended cement, and replacing up to 50% of the binder with these materials, which are abundantly available in different locations, would be promising solutions to ramp up this effort.
Yeah, I would add we're within the CS Hub ramping up a project this fall to try to become even more quantitative about that availability. Um, and as the comment about calcine clay indicates, and Hassam was sort of mentioning, there are other sources out there. I think that it'll be an interesting sort of research and market topic going forward to see how those be developed. The next question is kind of a LCA accounting question, so I know that Hassam will enjoy this. If CO2 for aggregate sequestration is captured from flue gas, wouldn't the sequestration count against the emissions from the plant from which the CO2 is captured, rather than against the emissions from the concrete or the asphalt application? I'll say production is the word here, but
this is a great question, and it's all to do with the well, for those who are not familiar with the technical aspects of conducting analysis, it's related to the system boundaries of our analysis and how do we account for recycled materials and the allocation approach that we will consider for our evaluations when we are talking about different byproducts in our system. In other words, we assume that for carbon capture, storage, or utilization here, the CO2 itself is a source of byproducts, and therefore we can have different assumptions to take into account the calculations, to take into account the savings that we can expect from this carbon capture utilizations. So if, for example, the allocation is based on the cutoff approach, we wouldn't attribute it to the previous industry, the flue gas part of the calculation, but we would definitely consider it in the material supply and for concrete production, which is the most conventional. But for recycled content or, for example, the other approaches that would take into account the recycled materials at the end of life, it would be vice versa as well. It's a very complicated and challenging part of the LCA calculation, but it definitely depends on where the source of CO2 comes from. We can generally capture the CO2 from the atmosphere as well. In this way, we may not need to be concerned about this allocation factor as well.
Excellent. So I'm going to answer one of these. Maybe Andrew could jump on. The presentation files will be shared. I think it's effective to some degree automatically through the system. Is that correct, Andrew?
Yeah, so this is being recorded, and then I'm going to be processing it myself. MIT has a requirement for closed captioning, so we'll be putting closed captioning on, and then we'll be sharing it through our listserv on either Friday or Monday. So you guys will have access to a recording very quickly after this presentation.
Okay. Thank you, Andrew. So we had a question if you could talk a little bit more about the savings that are possible or expected from using alternative binders. Yeah, there's sort of a related question, which is alternative binder and binder intensity the best policy or design code changes we could advocate for in sort of the more near term, say by 2030?
I'm sorry, what was the questions about how to account for the environmental impacts of binders?
No, like could you just comment more about how much? Well, the specific question was about the saving expected from using alternative binders, but my guess is that they're just curious about how much possibility there is, and then there was a related question about whether or not use of alternative binders and binder intensity are in fact maybe the one of the more high priority things to push for.
Sure. Yeah. So what is the concrete industry has been so much effort on that is the incorporation of the alternative binders, not only because of the environmental savings, but from an economic aspect as well. In addition to the better performance of the alternative binder incorporated mixtures. In other words, they have already evaluated that with the incorporation of these materials, we can improve the durability of the mixtures. And now it's been recently in the last 2 decades have been recognized that the embodied impacts of the concrete mixtures can be significantly reduced if we partially replace the Portland cement content by these alternative binder materials. And research and development have been geared toward increasing this replacement rate. And based on the projections in the short term, up to 40% replacement seems a viable solution up to 2030. But in the long run, up to 50% with some expectations and some limitations of the materials, would be some achievable goals or low-hanging fruit, let's call it, for the industry.
Um, I'm sort of looking at the clock and the number of questions. I'm guessing we're not going to get through all of these, but we're going to keep working as long as we can here. What do you think are the main barriers to reducing the binder content in cement and concrete for the U.S.?
I would first start with the opportunities, and then we can talk about the limitations as well. So the opportunities that I have seen so far is, first of all, thinking about improving the aggregates gradings in the mixture. Therefore, the aggregates can lock up each other very well and minimize the space between the aggregate. Therefore, we need less binder to glue them together, let's call it. Yeah, this is a great opportunity. The other opportunity that we can see is the injection of CO2 to the fresh concrete mixture. With that chemical reaction that we expect in that way, we can reduce the cement content without compromising the compressive strength or the durability of the mixtures. So the main barriers here that I can see is that the contractor or the manufacturer may need to have more, a number of available aggregates, for example, 2-3 types of sand to optimize the sand level, or 2-3 types of coarse aggregates to find the better solutions and to find the best proportion to optimize the aggregate grading. And the other part is the installation of the new equipment for this carbon capture and utilizations in the fresh concrete as well would be maybe a cost prohibitive option as well.
We got a question again. I'm not sure if this is our strongest area of expertise, but we'll learn what other things Hassam knows. So is there concern about the degradation of GTR, so ground tire rubber, in how it affects storm runoff and water, I guess, nearby water quality? Are there ways to minimize that degradation?
Well, this is really out of my area of expertise, but the only downside that I read about this GTR application is the increase in the stiffness and probably the problem that we may have related to the cracking because of the freestyle in asphalt pavements. So that's something that should be considered again when we are thinking about the incorporation of these recycled materials. We have to definitely consider the whole life cycle perspective and the performance of the mixture, as well as the environment, if there is any consequences related to the runoff or leachate, for example.
Yeah, it's probably important point also to mention that ground tire rubber, while it can be used as an alternative or sort of part of the binder in the asphalt context, it's also an alternative fuel for other processes like in the cement kiln. So I think there's an interesting open question about kind of the relative trade-off between those two applications, kind of from the bigger life cycle perspective. Let's see. We had a couple of questions that I know that Hassam can answer. So let me just throw that out there, and then maybe we'll just end with the last comment about the importance of life cycle. So one question was, how will climate change affect these kind of results? And a related one is that, EVs and, basically more efficient vehicles are going to be increasingly a part of the vehicle fleet. And have we considered this in our whole life cycle analyses?
Yeah, sure. So from the whole life cycle perspective for pavements, in other words, pavement LCA, the climate change impact the increase in the temperature in the future can contribute to a faster deterioration of the pavements. Therefore, we need more frequent maintenance and repair than what we are practicing now, probably. This is a consequence of the climate change related to the materials production and the materials consumptions for the road treatment actions in the future. From the EV part, we may have some savings if the EV electric vehicles energy is supplied from a renewable source for the in-use pavement impact. But again, these EV vehicles are heavier than a regular ICE EV, therefore we may expect a faster deterioration of the pavement. There are downsides and benefits of these technologies that should be considered from a whole life cycle perspective.
I would, but I would add to that, Hassan, that those are factors that we are considering in our overall network simulation model. So both climate change and the change in the fleet.
Absolutely.
I think we're sort of coming up against the end of the hour here, so I just kind of wanted to end with a final comment about that. We Hassan focused very much in this presentation on the important issue of reducing embodied energy, but he ended with a comment about the importance of the life cycle. And I just would sort of reiterate that to note that in the pavement system, making better choices about the materials and the design of those pavements can easily lead to use phase impacts that are on the same order, if not larger, than the embodied impacts. And as a matter of fact, as these solutions that Hassan talked about are implemented, that will become even more true as the embodied burdens reduce. So I think with that, I'm just going to thank Hassan again and thank everyone for attending. I'm sorry that we didn't get to all of the questions. I believe, Andrew, that those are recorded in some way or another. And so Hassan and I will try to reach out to folks as best we can to address some of the questions that we weren't able to get to. But thanks everyone for joining us, and we hope to see you back at another public webinar. Thank you.
Thank you, everyone.